Comments, questions? Yes, Dwayne. Do number 1? Number 2. I can do number 2. 2 masses are hung from a frictionless pulley. What is the acceleration of the 1.5 kilogram block and the 2 kilogram block? So here's question 2. It's this guy here. We'll draw the free body diagram. This guy's going to have Fg down. That's going to be 19.6 because it's going to be 2 times 9.8. There's going to be tension upward here. There's going to be Fg downward here. Now, 1.5 times 9.8. 1.5 times 9.8 is going to be 14.7. And we're going to have Ft up here. These two tensions are going to be equal and opposite. Which way do we want to call positive in this question here? Which way makes the most sense to call positive? Anybody? Sorry? Well, we've got, but, I mean, again, with the pulleys, you can't just say up. Clockwise. Clockwise makes the most sense. That's great because that 19.6 is bigger than the 14.7. If these guys move, the 2 kilogram will drop and the 1.5 will rise. So let's figure out what the accelerations of those blocks are. F net equals ma. And you want to start at the most positive side, work your way backwards. So we're going to have the Fg, I'm going to call this block 1, we'll call that block 2. Fg from 1 minus Ft plus Ft minus Fg2 is going to equal m total times A. The Ft's are going to cancel, and you're going to get 19.6 minus 14.7 is going to equal 1.5 plus 2 in brackets times A. So we're going to get, what is this? 4.9? Yeah. 4.9 equals 2.5A. You solve for A, you're going to get the acceleration is going to equal 1.4 meters per second squared. That is a universal, and that's the acceleration of both blocks in this system. It's important to distinguish that the 1.5 will rise and the 2 will drop, but the value here is the same. So the 1.5 kilogram block is going to go up at 1.4 meters per second squared, and the 2 kilogram block is going to drop at 1.4 meters per second squared. Does that make sense? Okay. Are there any other comments, questions, concerns about any? Yes, Dwayne? Number 1? I mean, 1's basically the same thing. You're going to have a free body diagram. We're going to have Fg here, Fn here, Ft here, Fg here, Ft here. And if this thing moves, it's going to move this way. So I'm going to call this way positive. You're setting up the exact same equation, except you're only going to use Fg, this Ft, and that Ft. These two forces aren't in the direction of motion of this block, so they would not be included in F net equals ma. Otherwise, it's the exact same as question number 2. You still want me to do it? F net equals ma. Start at the most positive end. I'll call this block 1 and this block 2. So it's going to be Fg 1 minus Ft plus Ft equals m total A. So what is that? 1.5 times 9. What's that? We already done that. 14.7. Those will cancel. Equals 2.5A. Solve for A and you're done. Three and 4 I assigned a couple days ago. It was the green ones circled here then. 1, 3, 4, 5, and 7. Is there anything there anyone wants me to take a look at? They're all very similar. Yeah, Brad?
Yeah, 2.
I didn't assign 2.
Oh, sorry, 3.
Okay. There's no space to do it there, so I'll do this one here. Ooh, 3, 4, and 5 are all related. 3, 4, and 5 are all good. It's the same situation. You've got bucket attached to a rope, so there's going to be Fg down, and there's going to be Ft up. It's a 12 kilogram bucket, so it's going to be 12 times 9.8. What is that, 119.6? 117.6. So, I mean, we could do all of 3, 4, and 5 right now. In question 3, if velocity is constant, so constant v implies a equals 0, means f net equals 0, so fg minus ft equals 0, fg equals ft equals 117.6. If the velocity is constant, that's it. And for the sake of this, I actually called down positive here because I had fg minus ft. That's question 3.
Oh, okay. I did it right, but I don't know. I already circled that out.
Okay. I mean, question 4 is going to be similar. It's accelerating upwards. So in question number 4, all that means is if I call down positive here, I'll keep that. I'll just say if it's accelerating upwards, the acceleration is going to be negative 0.6. So now the only difference here is that fg minus ft is going to equal 12 times negative 0.6. And then in question 5, the a is downwards now, 0.8. So it's going to be positive 0.8 meters per second squared, meters per second squared. So I'm going to get fg minus ft is going to equal 12 times positive 0.8. If you'd called up positive, then you just switch the order everywhere. It'd be ft minus fg, ft minus fg, ft minus fg. This acceleration would have been positive. This acceleration would have been negative if you'd called up positive, but I didn't. So that's 3, 4, and 5. So that's most of the homework I assigned. Question 1 is going to be the same as question 3. Question 7 is the only one that really, well, I guess question 7 from this one and question 8 from last week. No, last week? Was it Friday or Monday? I don't remember. Friday. Question 8 and question 7 are the only ones that bring in 2 ropes. Well, I guess 7 really is the only one that brings in 2 ropes. Are we good with 7, or does anyone want to see 7? Little clock day. Brain is dialed in today. Are we good with 7? And we don't need to see 7? Ray, we want me to see. Did you attempt 7? Okay, well then no. Then you're on your own. Okay, let's talk about it then. If you didn't do it, let's talk about it. Ray Reed, what are the forces acting on the 2 buckets in 7? Gravity is going to act on both of them. The FG downwards, that's going to be 196. And this guy's going to have tension acting upwards there. I'm going to call that FT2 because there's 2 different ropes, so now I need to label the tensions different. This guy here is going to have an FT2 downwards because that rope's attached there. He's also going to have an FG downwards. That FG is going to be 98, 10 times 9.8. And this thing's going to have a tension upwards, FT1. Bless you. They're at rest here, which is nice because that means accelerations, if they're not moving, acceleration's equal to 0, which means you can just start equating upwards and downwards forces. You know what? I'm basically done, so let's just keep going. We can figure out FT2 really easily because FT2, if that second bucket's not moving, the only forces acting on the second bucket are FG down and FT2 up. So these two have to be equal, which means the tension in number 2 has to be 196 newtons because it has to equal this one. And then the tension in 1, if we ignore the bottom block, and now I free body and isolate this top one, I've got FT1 is going to be balanced by these 2, the FG and the FT2. So that means that FT1 is going to have to equal FG, I'll call this, I'll call that 1, FG1, and I'll call that 2, FG2. FT1 upwards is going to have to equal FG1 plus FT2. So FT1 is going to have to equal the sum of 98 and 196. Whatever that is, 204? Is that even an option? No, 294. 294. 190 and 98 is going to be 180, and 14 is 294. Does that make sense, Ray Reed? Okay, that was all of the homework from yesterday. Took me 8 minutes. Love it. Okay, so here's what you guys are going to do for me today. You guys are going to do a pulley lab. I have this handout. I'm not just going to show you on the screen. I'm actually going to give you the handout. I'm going to talk you through it, show you the equipment, and then for you to work on it. This credit where credit is due. I snagged this lab from Mrs. Broad. She had her students do it last semester, and I thought it was really cool. So I'm going to bring it over here. You guys are going to need the following things. You're going to need a wooden block with a loop, the ones that are on the ground, like the big ones on the ground. You're going to need a tabletop pulley, which are on the front desk. You're going to need a meter of string, which I'll cut for you. A stopwatch, which you should all have on your smart devices. A 200-gram mass. Do not grab a 5. Make sure you have a 2. A meter stick, which I've got behind me over here. A 5 Newton spring scale and a 20 Newton spring scale. You'll need both. You're going to draw a free body diagram for me, and then you're going to start doing stuff. There's 3 pre-lab questions. The first one's the free body diagram. The second is what is Newton's second law for systems? And then third, write the forces that are going to contribute to this equation. And then you're going to start taking data. Now, you're going to be measuring weights, not using kilogram or gram scales. You're going to be using the Newton scales that we have. You're going to find FG1 for the wooden block, not using the scale, but using your Newton scale, not using the digital scales, but using the Newton scale. You're going to have to give me an approximate error for your value. It's impossible with the Newton scale. It's not going to be possible for you to get it exact. So how could you read it? And then what kind of error window, plus or minus what, do you think you could be within? Could be half a Newton, could be a Newton, and then explain why you think you're out by as much as you are. If you need me to come explain that when you have the thing hanging in front of you, I'm happy to do that. You're going to use the 5 Newton spring scale to find the force of friction on the wooden block. We've done this in a lab before. You're going to do it again, and you're going to use your desk surface for this because all the labs, it's all going to be done on your desk. You're going to find the force of friction. Just going to do it once. You're going to find the coefficient of friction of the surface of your desk. Give me an approximate error value based on the stuff that you've done for the force of friction and why you think that could be a reasonable error. Again, it's not, you don't want static. Do you want static? Does it say? What you need to keep in mind when pulling the wooden block? No, it's kinetic. You want the kinetic friction. You're going to set up the pulley as shown in the diagram on the front page. This diagram here. You're going to tie one end of the string to the wooden block. You're going to place the wooden block at the opposite end of the table to the pulley. You're going to put the other end of the string in the pulley and then tie the mass to the other end. So you're going to drop it over the edge. And you want to make sure the mass is at least 50 centimeters above the ground. So if you have to shorten the string to do that, shorten the string to do that. All of these desks are somewhere like 76 centimeters above the ground. The pulley is going to add some height to it. So you want to keep the mass up. Above 50 centimeters. You're going to hold the block in place. You're going to measure the distance between the end of the pulley and the wooden block. Check with me to make sure you've done this correctly. You're going to measure that distance. Again, include some error. How good do you think your measurement is? And why? You're going to release the block and measure the time it takes the wooden block to reach the pulley. You're going to repeat that 5 times. what makes answer this question. Using your knowledge of kinematics and the data you've collected, find me the acceleration. Using your knowledge of Newton's second law, your pre-lab and the data, solve for the acceleration. So you're doing it twice. You're using kinematics to solve for this, and F net equals ma. Find me the percentage error between your two acceleration values. And then what are the two assumptions that you made that are not true in terms of these calculations? It's the same assumptions we've been making this entire time, but I'll let you remember what those are. Talk with your partners if you need help with this. So you're finding the same value, the acceleration of the system, two different ways. And we'll see how those two values compare. As you're going, if you've got questions, let me know. You should be able to get this done. Well, at least all your data collection within the class period. If you've got questions, let me know. None of you should be, when you're doing this as a group, in 2s or 3s. 2, 5. I want all partners involved in every part of this exercise. Don't just leave somebody behind or say, I'll do this half and you do that half. All of you need to be involved in the entire thing. Brad. And your sister's still in this. Leaving her partners behind, just doing whatever she wants. She leaves her partners behind during group activities, just gets her part done for the day. Don't do that. Oh my gosh. Yes. One second. Let me get this started here and I'll take up questions. Okay. Make sure, I want to make something real clear, guys. When you're using these scales, something that hasn't come up yet, but definitely should have, you want to make sure that these things are zeroed. Okay? If this is what your scale looks like, the resting position of the scale is not 0. This one has a resting position sitting in like half a Newton, or 0.4 newtons, 0.4 newtons. You don't want to do that. This gray thing up here, you can slide up and down, not easily, you can push it down, so that this thing is actually 0. So that the floating bar actually starts at 0.
Excuse the interruption. At this time, could we have grade 11 students last
If
name
you've got anything
through that report to the staff room if you are interested in receiving the vaccination for HPV or any of your missing vaccinations. That's all grade 11 students, last names M through Z, to the staff room, which is directly across from the bistro for your vaccination. Thank you.
Anyone going to get shots? Okay, go down. Anyone who's partnering with Sire, don't leave behind. Go fast, Sire. Shots and come back. Okay. Everything you need is up here. Don't take anything you do not need. If you have any questions about how any of this works, let me know. You're getting shots too? Okay. Go fast. If you're getting shots, go quickly. Let's start.
This is supposed to meet?
Who? It is a meter, just over. Should I just wait for Sire then? Yeah. You get it up, get the stuff set up. There's pre-lab questions you can start answering. Just don't do any data collection without it. Okay. I will start cutting 1 meter lengths of string. Hey, Marcos, phone away. Don't leave me on. Nope, there's no applied force. It's gravity, friction, and tension. You're not the end of one, yes. No, it's not applied with the tension. You know exactly what it is. The reason that law proves is that the string is pulling on it. Henry, hello. How are you? Sure. Did you not get this last time? I just went over questions from the homework. The big one on the ground. You want the big wooden blocks on the ground, guys, not the small cubes. When you're, I have the string over here when you're ready for it. Oh, Brad, you grabbed the whole two sticks. Exactly the string. Take that, that's your string. How many more strings do I need to cut? Hands up your group. It's not low. It's not low. Okay. No, it's not. I thought I was good, and then turned out I was missing. I knew you were done. Anywhere else? Bro, I answered everything that he put. Who else needs string? Because you didn't need annotation for me. I was like, what do I do about it? I didn't know that. Yeah, no, that's why I told you. I was like, hey, you probably do that. But you're like, no, I'm fine. Yeah, and then Mr. Case on me and said, okay, if you're working with partners, none of you should be wearing headphones. You're working together, you're all involved, you're awake, you're hearing everything everyone else is saying. Marcus, if you're working with you guys. Sorry? Or you're ready for lock. I'm not sure that's a wise call. If he's not here by the time you're done those 3 lab questions, I want you to do this. Yeah, so that's kind of you to wait. But I'm not. Is that an A end or a O end? Should we be saying it's like 13 A and B? Should we say like, should we spell it first? You want like S little S? Yeah, well, that's fine. Use the notation that we've established in class, that's fine. We have established notation for a reason. If your work area is crowded, I got lots of open desks you guys can set up on. There's 5 of them right there. Lots of empty desks. Everything will be upright. Yeah. What do you mean everything? Well, I mean all the stuff that we just labeled here. Yeah. You got? Bro. Interesting. Okay. Yes.
Over here would just be like the times 9.8, right? Or
Yes.
yeah, so it would just be this one.
Yes. No. This one, 0.2 times 9.8.
200 tons.
Oh.
When he was asking what are the force that contributing, are we writing multiples or are we just, because if there's two tensions, am I writing tension twice?
There's only going to be one tension because there's only one string.
Okay, right.
But there's two FGs. So differentiate between.
Both of them in here,
We'll do both of them contribute to the motion of the object.
Yeah.
Sure.
Wait, no, because one of them is pointed down, right? Yeah, okay.
Guys, if you have multiple of the same kind of force, you have to differentiate them by calling, however you choose to differentiate them. You can call one block 1 and one block 2. So you've got FG1 and FG2. Kai, you are not supposed to be using digital scales for this. No digital scales allowed for this lab. It gives you instructions. It tells you how to do it. It says, set the 20 Newton spring scale for the vertical position. So use the 20 Newton spring scale. And find FG of the wooden block.
So just like this.
Yeah, just like that. Hold it up.
What I guess I'm sure it's 0. That's good. Yeah. Is it 0? Okay, let go of this. Let go of the block over there.
Because you want to check if it's 0 unattached. Check wall. That looks 0 to you? So you're measuring from the top, or do you want to measure from the middle, or how do you want to do it? Like that? Okay, cool. Let's see, yeah, good change.
I had it right.
Grab it from here so nothing falls.
I had it right.
Okay. Lachlan, good afternoon.
Alright,
Marcos has been waiting for you.
9 minutes.
What a guy.
Yep, 4 AAA batteries.
I do not have 4 AAA batteries. I can lend you a calculator, but I do not have 4 AAA batteries.
Yeah. What is it, 9? Okay. What is it? 9? Oh, yes.
Sorry,
It's exactly. Exactly 9.
Oh, that says yes, you're good. Yeah, you're good. Which FG is this? Because you have 2 FGs. So that's what it's doing. That's 1. Assume it's 200 volts. That will contribute positively to the air in your light. Same, I think I said the other week. When you have multiple FGs, specify which one's which.
Oh, FG1, FG2.
And there is no tension acting on the whole solution. Tension does not act on them. Tension acts on the blocks themselves.
What are we doing for constant error?
Okay, so
Well, I don't know why they always.
so here we go.
We said 9 newtons.
Is exactly 9. Okay, so Kale says about 9 newtons. Plus or minus what?
I'd say plus or minus.
Okay. Because holding it here in front of me, I see it as being like 8 3/4, maybe. Doesn't seem to be right down there at 9. So like, and it's because it's bouncing depending on the stability of your hand, how long you hold it. Don't hold on back. Like you just don't really squeeze the plastic. Like you hold it from the hub.
Hold it exactly still.
And remember, you centered it so that it's the middle of this thing was at 0.
Yeah.
So it's in the middle of that thing that you want to measure. Is it right at 9? Is it 9 and a bit? Is it just under 9? Okay, so then ballpark what we feel like it is. Okay, so and now he's giving an error. How is it moving around? What do you think? Is it like a quarter of a newton? Is it 10.2 of a newton? You only need interesting. Okay, which one were yours? Why do you have more blocks? There's one of those lamps. Oh.
calling you.
I got my motorcycle.
Let me go.
Grab one of those. I got my
Three
motorcycle.
there, they'll all have like
in
this.
October.
Make sure you put the one that you take, put it back where you got it from. So you're working with the Atlanta, that's the one you shot.
So I thought it was only because money after the bill.
Okay.
Like, all you gotta do is pull up side. You gotta study, right? You just show how you date. It's probably harder. I don't think the test is as accurate as the website.
Sorry?
I went in there for the car.
Yes.
Motorcycle. I actually it took me like half hour. But I passed. Yes. Realistically, bro, I'm not getting. I'm not gonna be able to ride for like 2 years. I actually have to buy myself like. And I have to actually learn. It's gonna be a while.
What kind of bike do you want to get, Kai?
I haven't looked into it because there's no point.